Have you ever stopped to consider the universe teeming with life inside your own head? Billions of neurons fire in a complex, silent symphony every moment of every day. They create your thoughts, your memories, your dreams, and your unspoken words. This inner monologue, this private conversation you have with yourself, is perhaps the most fundamental part of your identity. But what if that universe became a prison? What if the bridge between your inner world and the outer one collapsed, leaving your thoughts trapped in endless silence? This isn't science fiction. For many, it's a stark and isolating reality. Imagine having a mind as vibrant as ever, but a body that refuses to communicate. So, how do you build a bridge to the mind? The answer lies in brain-computer interfaces, or BCIs. Think of a BCI as a cosmic translator. Your brain speaks the language of electricity and chemistry, while computers speak in bits and bytes. A BCI stands in the middle, listening to the brain's electrical chatter and translating it into commands a computer can understand. At its simplest, a BCI might involve wearing a cap that detects brainwaves from outside the skull. You think "move up" and the BCI detects the shift in electrical activity. It's like trying to listen to a single conversation in a roaring stadium from a blimp flying overhead. Advanced systems place tiny sensors directly onto the brain surface. This is like moving from the blimp down to a front row seat with a microphone. Suddenly, you can hear individual neurons firing and detect the precise patterns that represent specific thoughts or even speech sounds called phonemes. This is where Stanford University made a cosmic leap forward. They asked, what if we decode the brain activity for speech itself? As you silently say words, your brain's speech centers light up with activity. The motor cortex areas that control your tongue, jaw, and lips fire commands even when muscles can't execute them. The symphony is playing, but the orchestra is silent. Their system uses small, high-density electrode arrays placed over the speech motor cortex, incredibly sensitive to faint electrical signals. The real magic happens in the software. A sophisticated AI algorithm translates raw neural data trained to map neural patterns to phonemes, the building blocks of words. By decoding phonemes in real time, the system assembles them into words and full sentences, spoken aloud by a computer-generated voice. This leapfrogged previous text-based systems, aiming for the natural rhythm of human conversation. To understand the human impact, meet Pat Bennett, diagnosed with ALS years ago. ALS gradually took her ability to speak, trapping her vibrant mind within a silent body. She could communicate, but only through slow, laborious methods. Her world had become quiet. Stanford scientists implanted tiny electrode arrays onto Pat's brain over the region responsible for speech. Then the training began. Pat was shown sentences and asked to try saying them silently. As she did, the BCI recorded neural data. The AI listened repeatedly, learning to associate electrical storms in her brain with specific words and phonemes. The results were breathtaking. As Pat silently formed sentences, words appeared on screen at over 60 words per minute, 3 times faster than previous methods. For the first time in years, Pat's thoughts could flow at a speed resembling real conversation. It was a profound reconnection, a bridge rebuilt between her inner universe and the world outside. Communication is the foundation of our relationships and sense of self. Language is how we share joy, express sorrow, and tell stories that define who we are. When someone loses the ability to speak, they risk losing their connection to the world and their role in their family. Imagine the simple moments lost to silence, telling a spontaneous joke, whispering "I love you," or comforting a child with your own words. A BCI that restores speech gives these moments back. It reopens the door to spontaneity, intimacy, and connection. By giving them back their voice, we give them back control and dignity. This technology is still in its infancy. Current systems require invasive brain surgery, a significant procedure with its own risks. Right now, this is highly specialized and expensive, available to only a handful of research participants. How do we democratize this technology and make it accessible to millions who could benefit? Could we develop non-invasive BCIs with the same precision, perhaps using focused ultrasound or advanced magnetics? Imagine a future where communication isn't limited by physical ability at all. What about applications beyond medicine? Could an architect think a building into a 3D model? Could a composer think a symphony into existence? We could be on the verge of a new renaissance, an explosion of creativity unlocked by direct interface with human imagination. We stand on the precipice of a new era. What happens when we develop the capacity to bridge the final gap between minds? The next chapter of human evolution may not be written in our genes, but in the connections we build. The Stanford breakthrough is more than technological triumph. It's profound liberation. For every person trapped in silence, this research represents light in the darkness, a promise of reunion with the world. We look at the stars and build telescopes to see farther. Now we look at the mind and build interfaces to listen to its silent song. It's all part of the same grand human adventure, the quest for knowledge and connection. What will happen to humanity when the universe inside one mind can connect directly with the universe inside another? The next chapter of our story is just beginning.